And essentially, just to recap what this project was and is, was a piece of work to look at salinity guidelines in Alberta. Obviously, we manage most of our salinity, at least in the top meter and a half, based on EC. The majority of our salinity issues in the province, as we all know, come from sodium chloride, either from produced water or from road salt. But we do have sulphate issues, from sulphur handling facilities and the like. And so we've always assumed that the same guidelines, we'll just use those same EC guidelines for chloride and sulphate. But the EC guidelines that we work with are very much based on, well, they're based on plant toxicity, but all of those tox data, it's all chloride data. And so we were trying to answer the question: is there a significant difference between the toxicity of chloride and the toxicity of sulphate? So just to acknowledge our funding, of course, this was from generous funding from PTEC, but out of the 2012 budget, and we're still sort of wrapping it up now. As I mentioned, I mean, we do have we've got a lot of sodium chloride issues in the province, as we all know. Our anthropogenic sulphate salinity is, at least from my experience, primarily related to sulphur storage and handling facilities, which, while they may not be that great in number, the ones that are around there, they're big sites and they're significant, so it's worth putting some sort of level of effort into this. So, overview of what I'd like to talk about this morning. Just briefly introduce or talk a little bit about the basis for our existing EC guidelines in the province of Alberta, and then to step through a process of looking at what we already know and what we found out in this project on the relative phytotoxicity of sulphate versus chloride. And so, very brief summary of a literature survey that we did, and then the experimental design that Darlene and I worked on together, and then spending a little more time on our results and analysis and drawing a few conclusions. So in terms of the basis for our existing Alberta EC guidelines, they're obviously based on plant growth. But for those of you who recall that, they are really based on a document that came out of Alberta Environment in 2001, I believe. And that just predated the current approach for developing guidelines for what we call the eco-contact pathway, or the ecological direct contact pathway to protect plants and soil invertebrates. What we've been using for the last, let's say, since the Canada-wide standard of hydrocarbons came out in 2001-ish, so for the last 13, 14 years, is this species sensitivity distribution approach. And so I just wanted to make the distinction that pretty much every other eco-contact guideline in the Alberta Tier 1 guidelines is based on that species sensitivity distribution approach. But our existing eco-contact guidelines for EC kind of predate that, and they're on a more of a semi-quantitative approach that was appropriate at the time, certainly. And that approach considered literature data on plants. It was all salinity data, but it was all essentially sodium chloride. So here's, no surprise to anyone, here's our Alberta EC guidelines. We distinguish between topsoil, which in this context is considered to be essentially the A horizon plus the LFH and organic horizons. So essentially the agronomic soil, if you will, and subsoil, and we have a range of EC guidelines based on where the natural salinity and background is. And so, for soils where we don't have a natural salinity issue, we've got a guideline of EC of 2 in topsoil and EC of 3 in anything below that top layer. That SCAR document, that 2001's Alberta salinity document, it did a very good job of pulling together and summarizing a whole bunch of salinity data. But in practice, what was really used were these USDA salinity tolerance relationships. And the USDA looked at a whole bunch of salinity data and tried to simplify that for each plant species that they considered into a threshold below which there wasn't really any effect on growth. and then a slope of decreasing growth with increasing EC. And then just to drop in how our characteristics of salinity that we use in Alberta slot into that. We characterize our background based on good, fair, and poor, and unsuitable, and just showing how those fit in with those USDA data on which those guidelines are primarily based. Before we started into this process, we thought we'd have a good look at the literature and try and get a sense from the literature of where there were data that would allow us to determine, allow us to compare directly the phytotoxicity of chloride and sulphate. And of course, all of these studies were being done for their own purposes, which generally wasn't the same thing that we were looking for. But as far as it was possible from each one of these studies, we made a determination of whether there were studies which exposed plants to equal concentrations of chloride and sulphate, and pulled out a conclusion from each of these studies. And as you can see, it's a mixed bag of the, is that 11 studies there? One of them showed that sulphate was, that the plant species in question was more sensitive to sulphate than chloride. 3 of them were kind of ambivalent, and 7 out of 11 indicated that chloride was the more toxic of the 2 ions to that particular plant species. So that gives a sense going in that perhaps sulphate was less toxic than chloride, but certainly nothing we could take to the bank. So we decided to initiate some experimental work using sort of what's come to be our standard procedure for developing guidelines in the last sort of 12, 14 years. And we took what's now the standard 3 plant species. We've all heard this before. Our alfalfa, barley, and northern wheatgrass, which we've used to base many guidelines on. And we're using those standard Environment Canada test protocols, so everything's up to standard. And we're using 2 soils, both of which were natural soils from Alberta. So as far as possible, we're now collecting data that is the most relevant possible to setting guidelines in Alberta. And then the bullet at the bottom there, we're conducting 2 exactly identical experiments, parallel eco-toxicity test sets, one with sodium chloride and one with sodium sulphate. And then first and foremost, we're trying to see, well, do we get essentially the same result with both, or do we get a different result? So there's a nice photo courtesy of Darlene. Typical plant toxicity test sort of thing. At the back, you've got the controls and increasing salinity as you come forward to the point where at the front there's nothing growing at all. This I thought I'd throw in, not because it's directly, we needed to do this for our work, but I thought these data might be useful to other people, so I thought I'd explicitly put them in the presentation so they're available. What this is, for each of those concentration series, we measured the ion concentrations, and we also measured EC, and that enabled us to develop the relationship between EC and chloride or sulphate concentration. And quite often in doing sort of salinity type work, we do want to be able to convert between EC and ion concentration. Those, as we know, those relationships do depend on soil type, but this enabled us to see what those relationships were separately for chloride and sulphate and separately for the 2 soils that we tested. And I just put the regressions in here in case anyone would have a use for those going forward. I expect this sort of thing. You're 6 months' time, you'll be looking for that relationship, and so hopefully those will be available. So back to the main thrust of what we're trying to do here. As I mentioned, our standard approach for developing guidelines from Eco-Tox data is to develop this species sensitivity distribution. I'm sure almost everyone's familiar with that concept in the room, but let me just step through it quickly. So essentially, for each species and endpoint that's in your toxicity test data set, so for instance, one endpoint would be the shoot, the shoot length growth for alfalfa. Another one would be the mass of roots in barley. And each of these data points is the IC25, so the concentration which causes a 25% reduction in that endpoint. So we take those. So we've got 3 plant species, 4 endpoints for each. That makes a total of 12 data sets. So for fine soil, and then we rank them in order and we plot them on a graph. So for fine soil for chloride, that's the sort of distribution we get. So at some number like 700, we've got almost none of those endpoints being affected, and up at 2,500, milligrams per kilogram chloride, we've got most of the endpoints being affected. That's the one for chloride in fine soil. If we drop on the chloride coarse soil, we see they kind of crisscross over a couple of times. I can't say those lines are distinct. I don't think the difference between them is probably meaningful. And so my feeling is probably the best thing to do for chloride is combine those data sets with the green line there and say, okay, that's the species sensitivity distribution for both soil textures for chloride. And this is, we didn't have quite all the last data sets last year, so we weren't able to draw these SSD curves. And as we mostly know, once we've got those SSDs, we look at the 25th percentile, at least for the most land use for natural area and for agricultural, the 25th percentile, and that gives us, reading off the graph roughly something like 800 milligrams per kilogram. And so if we were using our current guideline setting methodologies, that's how we would pull an eco-contact guideline for the chloride ion out of this data set. Looking at sulfate here, same sort of thing, but you'll notice that the numbers are rather large, and now we're talking about a range from 2 to 8,000. That's the fine. That's the SSD for sulfate in fine soil. Now here we see the difference. So now we see sulfate interacts differently. It has a different SSD for coarse and fine soil. And we can talk about that if there's questions. But essentially, our assumption is that chloride interacts pretty minimally with most of the soils that we deal with, whereas there's far more things that can go on once we've got sulfate in the soil. And I think that's what's happening here. We've got two different soils, two different sets of interactions, and the sulfate in the fine-grained soil with a higher clay content is probably less available to the plants. We could combine those as well, but it looks, for the case of sulfate, like it's reasonable to treat the coarse and fine soil results separately. But the real driving rationale for doing this project in the first place was to compare chloride and sulfate. So if we do that, we can pull out the guideline values for probably separately for coarse and fine-grained soils for sulfate, and we're up in the sort of 2,000 to 3,000 milligrams per kilogram range there. Now, this is really the interesting guideline, the interesting graph, interesting image out of the whole project. This is the combined species sensitivity distribution for chloride compared with that for sulfate. And what we can see is here, these two lines are unequivocally different. Sulfate, the guidelines that we would generate for sulfate on an ion basis are 2 to 3 times higher than they would be for chloride. That's not totally unexpected, because as we know, the mass of a sulfate ion is probably a couple of times that of chloride, 96 over 35, whatever that is. But if we take those, this image demonstrates clearly that there is a difference in sensitivity to those two plants, to those two ions. And then if we turn that into numbers, now there's two ways of developing guidelines from these data sets, and they both have applications. They're both useful. It is handy to be able to say, well, how many milligrams per kilogram of chloride would I have in my soil before I'm starting to impact plant life at a concerning level? And so, pulling the numbers out of our data, we come up with 840 for chloride, and then in either soil, and then 2,200 and 2,900 milligrams per kilogram for sulfate in coarse and fine soils. We'd expect to see a much smaller differential between the guidelines that we would calculate on an EC basis. So the EC guidelines, that's saying, okay, our salinity is based on chloride or sulfate, but we're going to measure it based on the EC of the soil. Because of the difference of mass of those two ions, the difference we'd expect is much lower on the conductivity, but there is clearly still a difference. And so if we use the species sensitivity distribution approach to calculate an EC guideline, if we use chloride, we come up with a guideline of 5.3 decisiemens per meter. And if we use sulfate, the number is 8.3. And just to be clear, all of the numbers I'm presenting here are guidelines for what we call sensitive land use for natural area and agricultural land. The full report's got guidelines for commercial industrial land use, but I just haven't presented them here. Just for clarity. So that's really what I have. So in conclusion, this project developed relationships for Alberta soils between EC and the chloride ion concentration and EC and the sulphate ion concentration. We developed soil quality guidelines for chloride and sulphate, and just to be clear, these are guidelines based on the SSD approach, the species sensitivity distribution, which is our current method of developing guidelines, but is not consistent with the way that the current EC guidelines are developed. We developed soil guidelines both on an ion concentration basis and an EC basis. And we concluded that sulphate was significantly less phytotoxic than chloride in our battery of tests. And therefore, the corollary of that would be that it would be a reasonable approach if you're dealing with a site where you know the salinity is all sulfate-based to take perhaps a different approach from just the straight chloride-based toxicity approach. Next steps for this research, I'm hoping there's going to be an opportunity to discuss this with the regulatory community and see what makes sense as a way to incorporate this new understanding, new knowledge into our regulatory framework going forward.